All right. So, welcome to the panel on the grid of the future. Thank you all for joining us. Hoping that this is going to be an informative session. It's going to build on some of the topics that we've discussed already this morning. Some of the importance around decarbonization in our grid. We've talked about topics around electrification. Really, the goal of this session is to take us from the more theoretical level of decarbonization down to a more practical level of what does that actually mean? What does it mean for our system? What does it mean for consumers? Big thanks to Chris Skokeland with New Hampshire DES for pulling this together, really the brainchild of the session. My name is Matt Siska. I'm with GDS Associates. I'm going to be your moderator for the session. A little bit about me. I work for Energy and Engineering Consulting Group. I run a commercial industrial services team. Our team is really right now based on providing beyond lighting technical energy efficiency support in the C&I sector. We focus on high performance buildings. We focus on building controls, on electrification, on storage, a lot of the kind of topics that we've been talking about this morning. The reason that we focus in these areas because this is where we see the region going. We see the grid evolving in this way. I have also some responsibility for overseeing a team that provides a lot of regulatory support. We do benefit cost analysis, energy efficiency programs. So I'm involved in a lot of the policy side, and that type of kind of broad experience is, I think, why I'm here moderating the panel for you all, and really interested in these topics. So we've got a couple of great speakers. We're going to get to two presentations, and we'll do hopefully a fairly lengthy Q&A at the end. So like I said, this session really the goal is to dive into some practical topics, things like power supply, the importance of maintaining reliability in the system. This is a topic that we've touched on early. How are we going to reach some of these decarbonization goals while maintaining system reliability without pricing consumers out of the market? We see the grid evolving in a number of ways to be able to achieve this push towards decarbonization with increased electrification that's ultimately going to increase our overall system loads as well. This is going to prevent a lot of challenges, but also open up a lot of opportunities. I wanted to start and just try to get a bit of a pulse of kind of your knowledge around some of these issues. How many people in the audience are familiar with the term the duck curve, the ISO New England duck curve? Okay, excellent. So we're talking about the prevalence of daytime solar and then that kind of sharp ramp back up of the system load. Once the sun starts to go down, people are coming back from work. How many people in the audience are familiar with the term resource adequacy? Okay, not as many. And that's going to be a really important term, and this is something that, that Dr. Mettetal is going to talk to us about as well. Resource adequacy really talks about the need for the system to have sufficient capacity available to meet the load at any one time. What we're seeing in other states, California is one of the leaders right now, is that they've got massive issues associated with that ramp period from 4 to 8, 4 to 9 o'clock at night. When the solar resources stop producing, loads go up and they need fast reacting generators to be able to provide that capacity. Having that capacity under contract tends to drive a lot of costs and is really kind of a very important balance here between supply and demand as we move towards greater penetration of renewables and kind of the need to maintain system reliability. Dr. Medital, and I'll introduce her in a second, is going to be talking about a study that she presented or helped to author regarding pathways to decarbonize the New England power grid. Looked at a number of different scenarios, different types of supply resources, the importance of reliability. She'll be going through those topics for us. And then I'm really pleased to have Brian Callnan with the New Hampshire Electric Co-op is going to be talking about more the perspective from the distribution utility. How are they preparing for this grid of the future. And he's going to be talking about their transactive energy rate pilot, which is a kind of a market-based mechanism that they're going to use to help customers shift load from higher demand periods to lower demand periods in a way that kind of benefits both the grid and will ultimately be able to benefit consumers as well. And it's really more of a kind of an in the field type of perspective of how the distribution cooperatives are looking at the grid of the future. So with that, I'll introduce Dr. Liz Mettetal. She's a senior managing consultant with energy and environmental economics based out of Boston. Dr. Mettetal is an experienced energy economist and project manager with E3's clean energy and resource planning practices. Her work enables utilities, companies, and regulators to support the clean energy transition. Recently, she managed a study to evaluate electricity sector reliability under resource portfolios consistent with New England achieving economy-wide net zero greenhouse gas emissions. She's also managed some recent support for Nova Scotia's development of a long-term electricity resource portfolio that achieves similarly ambitious RPS targets. Prior to E3, Dr. Mettetal spent 4 years in energy and environmental consulting at ABT Associates, NERA Economic Consulting, where she oversaw and performed economic analyses for utilities and federal agencies. Topics related to energy, natural gas, water, waste, air quality, climate change, and transportation. So without further ado, I will introduce Dr. Mettetal.
Thank you very much. Thank you very much. Thanks, Chris and Matt, for the introduction and for organizing this session. So my name is Liz Mettetal. I'm a consultant and project manager at E3 based in our Boston office. And today I'm going to tell you about work my colleagues and I did in New England looking at net zero. So, we're going to be giving you the sort of high level looking backwards, what the system needs to get there. And then I'm looking forward to Brian telling us how he is working on changing the way we enable customers on the grid today. So I think it's useful to just start really briefly with the why. So scientific consensus has shown basically that global warming is occurring on truly an unprecedented scale. So I think the IPCC, the International Panel on Climate Change, calls this unequivocal that the climate has already warmed more than 1 degree Celsius, and what we know is that reducing the risks of climate change requires limiting warming. So, reducing the impacts we're feeling already in New England is going to require keeping things within 1.5 degrees Celsius. And so what we know is our best shot at doing that is getting to net zero emissions by 2050 or mid-century. And what we mean by net zero is that all emissions emitted, so any greenhouse gas emitted, would be offset or removed through some other means by mid-century. So today, what we know is that, many of the states in New England are pursuing a range of emission reduction strategies and setting targets and goals to help move us towards that deep decarbonization target. So, most of the states have, and they're structured differently, but emissions reduction targets or mandates. Massachusetts is about 45% or 44% of New England's emissions, and they are achieving net zero. New Hampshire has talked about some goals and worked on a climate action plan, but doesn't have one legislated at this point. And then most of the states have, actually all of the states have RPS targets, as I'm sure you all are aware, to basically increase the portion of renewable generation. So all of these are going to help basically move the region towards net zero. But that said, they won't be enough to get us there. And so what I'm going to talk about today is the study that E3 performed with our partners at Energy Futures Initiative, so this is Ernie Moniz's organization, and the work was sponsored by Calpine, asking, how can New England provide affordable, reliable electric power under scenarios that are consistent with a net zero economy-wide target. So this was a very large effort. You can see the 100+ page report online, and there were many sub-questions that were addressed through the course of this work. So, what are the decarbonization technologies and strategies that are going to get us to net zero at an economy-wide level? How much is the electricity sector, as a key emitting sector, going to have to reduce emissions? And at the same time, the electricity sector is going to have to support and meet a whole lot of new electric load due to the electrification of buildings and transportation by mid-century. And we know, of course, that the shape of that load is going to matter a lot, and how it contributes to peak impacts. And then, what is the optimal electricity resource mix? And by that, I mean sort of the lowest cost, subject to a variety of constraints, operational constraints, reliability constraints, emissions constraints, to meet all of these needs by 2050. We looked at, the ability of different supply side resources to achieve resource adequacy and maintain a reliability standard. And then, what are the implications in terms of the need for innovation? So obviously, given the time we have here today, I won't be able to go through all of the methods and analysis that was done as part of this study. You can find it on our website. But I'm going to try to hit on some of, I think, the key findings, kind of focusing on what we found. So I'm going to jump in. All right. So we started with a economy-wide pathways model, and what this is a model that basically reflects all infrastructure and energy emissions within the economy of New England. And we have a stock rollover model. So, over time, households purchase new space heating and cooling equipment. They buy new cars. They replace their appliances. And over time, that has impacts on emissions. And so, you play out a reference case to 2050, and then you say, okay, we need to get to, in this case, we said an 85% emissions reduction relative to 1990. So, here's where we need to be. What does that imply about sales and emissions for various, for all of the energy emitting sectors of the economy over time? So that's kind of what we did. What I'm showing you here is what has to happen to New England's regional emissions over the next, 30-ish years. So if you looked off the table, in 1990, emissions were around 200 million metric tons. And so we model net zero as achieving 85% direct emissions reductions from that 200. So that gets us to 30 million metric tons by 2050. You can see, as of the latest, benchmarking, we've made some progress. A lot of that is, huge emissions reductions, about 50% emissions reductions in the power sector, largely from switching from coal to natural gas. But we still have, 70+ million metric tons of transportation emissions, 30 million metric tons of power sector emissions, and then significant building emissions, and then industry and some non-energy emissions. So all of those, we have to reduce dramatically by 2050. So in the study, we modeled two main scenarios. So one assumes really significant electrification, and I'll call out some of those measures on the next slide, but it essentially assumes that, the region aggressively, and this would be sort of consistent with the US or globally, really largely electrifying buildings and transportation, and essentially, more limited market development of advanced to low carbon fuels, so things like hydrogen or advanced biofuels. We then ran a second scenario that was saying, well, if electrification is too expensive, not technically feasible, then you might end up in a future where you're relying much more heavily on advanced biofuels. Both of these are big changes from where we are today, but they essentially reflect a range of implications for the electricity sector, which was, the focus of this work. So um, the two scenarios, basically, one is going to have much higher electric loads, one's going to have lower electric loads, but both achieved a 85% direct emissions reduction economy-wide. And for the electricity sector in particular, assumed that 95% of megawatt hours were carbon-free by mid-century. So in terms of, what does that decarbonization pathway involve? So here I'm just showing for the high electrification scenario, which I would say is where a lot of the policy conversations have been going. So given the long lifetimes of, equipment and infrastructure, what we know is that we need to be beginning today to get to those targets by 2050. So in the 2020s, we know that we need to be ramping up sales of electric vehicles on the light duty side. We need to be aggressively pursuing energy efficiency and efficient appliances, building retrofits, weatherization, and then electrification of space heating through heat pumps and water heaters. We know by 2030, so in our scenarios, in a scenario consistent with achieving net zero, 50% of sales of space heating sales would need to be heat pumps by 2030. In a high electrification future, it's a little bit less, 30%, but much higher than today, even in a high fuels future. For light duty vehicles, that's LDVs, 70% of sales would have to be electric vehicles. So we'd all have to be out there, not just test driving, but buying electric vehicles. Similarly on the medium duty and heavy duty, those would have to be transitioning to electric. And our power sector would need to be around 2/3 clean by the 2030s. Now, by mid-century, the economy in New England would need to be really entirely transformed. Nearly all sales would need to be heat pumps. 2/3 of buildings would have, efficient building shells, basically all new buildings, plus some retrofits. We know that, basically all electric vehicle sales, also EVs, and then 95% of electricity would be coming from clean resources. So renewables, nuclear, hydro, any zero carbon resource. So the transition starts now. So in a world where we're on a path to net zero, which is, where I think policy wants us to be today, we know that electricity demand would, by mid-century, nearly double. So, in a world where basically everyone's driving an EV and, all new space heating is heat pumps, loads jump up quite a bit. But as, electricity planners know, what we really care about is what happens to peak demands, because we're going to have to build our system to meet that peak. So in our modeling, we get the system switching to becoming winter peaking by the early to mid 2030s, depending on the the high electrification or high fuel scenario. And so what that means is that by 2050 we're getting to a winter peak. So this is on the lower left hand side of around between 40 and 50, but that upper blue bar is in a high electrification future. It could be 50 gigawatts by 2050. And what I want to call out is this is after assuming huge amounts of load flexibility, managed charging, and a really what we like to call smart building electrification. So a lot of, I think, we have 20% ground source heat pumps, and then the rest, most are air source heat pumps, but about 40% of those maintain their fuel backups. So they're using, their existing gas or oil for the coldest winter days of the year as a way to mitigate the peak. We're also basically modeling kind of all of the weather variation within New England to try to say that, not everyone is going to experience the peak at quite the same time. So, how can we basically lower that peak load? This also assumes that, 70% of light duty vehicle charging is flexible. So essentially, time of use rates or, managed charging through some sort of V2G is basically limiting the impact on peak. We're still seeing, really huge peak impacts. Though I'll note, other net zero modeling studies in New England are seeing even higher numbers. So what does that mean in terms of electricity sector capacity? Well, it shouldn't come as a surprise now that, new capacity additions, one is to meet the increasingly stringent power sector target, so an emissions limit that we've put on the power sector. You're going to be building lots of renewables. The economics of renewables are also improving over time. So, in our high electrification scenario, we're getting 22 gigawatts of utility scale solar and 22 gigawatts of offshore wind, around 7 gigawatts of onshore wind. The implications of this are huge, right? That's, it's like 800,000 acres of wind, 150,000 acres of solar. So within New Hampshire, that could be, 17,000 acres of solar and 100,000 acres of wind. So it's a huge amount of land area potentially. I mean, there are ways to do it smart. We've talked about some of them in this study. Rooftop, all of these other of ways of siting renewables, but there is going to be a huge infrastructure implication of this type of build out. I'll also note is that our system does maintain some gas capacity and builds some gas capacity, and that's to meet those reliability requirements. Basically, the reliability challenge that we found in our study was, really shifted to the coldest winter days. So January, February in our simulated weather years. And it was basically, we would get outages in our loss of load models after, long periods of low renewable output. So when you have, 3 cold days in January where, you have low solar and wind and you basically run out of batteries discharging. So, our system basically maintains some gas capacity, but as the generation graphs show, it almost never generates. So it's really there as a capacity resource rather than as a source of energy in our modeling. So in order to meet our emissions targets, generation becomes about 95% carbon free by mid-century. And it's really dominated by renewables. I think 60% of that generation is renewables. There's also some imports. We do show that our modeling in a least cost capacity expansion model optimization that another 2 gigawatts or so of Hydro-Quebec imports would be cost effective through turbine upgrades. We also show that either keeping nuclear online or repowering is, cost effective. So, I mean, those are policy choices, but, that is in our base modeling case how we get to 95% carbon free. And I wanted to note here, so we, in the study, if you go look at the paper, we ran more than just 2 scenarios and we varied, the sets of assumptions and constraints on those different scenarios. So the base case I show you on the left, that you're basically, we were building, 22 gigawatts of solar and offshore wind. If we assume that land is more constrained, so I mentioned, that, this is building, hundreds of thousands of acres of renewables. The model would choose to just build a bunch more offshore wind. If you unconstrain land use and you allow the system to, build as much renewables as it wants, it builds more like, 44, 45 gigawatts of utility scale solar, which is just a really cheap becomes over time a really cheap source of energy. If you assume unlimited advanced nuclear, so small modular reactors or the like. You can, the system costs go down, you can build less renewables, and you might build, up to 12 gigawatts in our model of small modular reactors. If we assume CCS is available, and our assumptions around CCS are based on, cost projections from NREL and the assumption that we would have to pipe the CO2 out of the region given, a lack of geologic storage within New England. You can also, the model would choose to build 11 gigawatts. And if you assume both are available, it'll build, a lot of nuclear and a little bit of CCS. And these would, lower overall cost to the system. But again, there's trade-offs. So what this graph shows is just how the total system costs change. And, we have basically a partial system cost estimate. So this is why we're kind of reporting things relative to a reference case. So our 2050 reference case was a case that hit a 50% RPS and ended up with around 27 million metric tons of emissions. Compare that to the 32 million metric tons of emissions in the power sector in 2016. But if if we want to reduce the emissions further from that, so if we hit a 10 million metric ton target, then, costs go up, a couple $billion. And then, you can keep going along that blue line. The kind of base scenario I had been showing you is when the electricity sector is hitting that 2.5 million metric tons. And then if we don't allow new firm capacity to help meet that new load, you can see the green dot is basically the increase in system costs doubles. So you have about a $10 billion cost increase because you just have to build more renewables, which have limited firm capacity, basically effective capacity credits. CCS and nuclear, again, these are opportunities to lower costs. And then if we remove all firm capacity from the system, the cost really explodes, just about $20 billion annually relative to a case that does keep some firm capacity online for those, basically the coldest winter days. So I'll just note at a high level, I don't want to take too much time, but I think if it's not apparent already, there's just huge infrastructure implications of decarbonization for New England. If we're going to meet 50 to 60 gigawatts of renewables, 10 gigawatts of storage, then that just these are regional needs and would require, as I said, hundreds of thousands of acres of land. I think something we get into in the report and but haven't really talked about that much is, transmission is going to be really important. Transmission costs are really what drove our model to sort of build in different parts of the region and to try to avoid those costs because, they're definitely a significant cost hurdle. But, we estimated, could be up to 3,000 miles of backbone transmission required, as well as transmission to Hydro-Quebec, just to basically connect those renewables and support delivering all of this additional power. And then, of course, as we talked about up front, electrification also has huge infrastructure requirements, everything from the public charging infrastructure to building retrofits. As Brian is going to talk about, there's also, really, kind of exciting and challenge, but, the grid is more and more customer focused and, we're going to have to integrate all of these DERs and, both upgrading the T&D system and, changes to rate structures and that kind of thing to move the needle. And so I'll just note too is that, regional innovation, is also opportunity, right? Meeting these mid-century targets is challenging and requires a lot of investment. In our report, we talk a lot about the sort of exciting innovation capacity that we have within the region already to address these challenges. And I think it's a really exciting time to work in the clean energy space. Um, and so, yeah, so I think I've covered all of these key points, but, electricity demand is going to could double basically to help meet this net zero target. If the region is to achieve net zero, and that's even with huge amounts of energy efficiency and conservation. Um, we know that a lot of renewables are going to be built across a range of scenarios and assumptions, and that land availability and transmission availability and costs is really going to be sort of key constraining factors on how that build out happens. We know that there are a lot of exciting low carbon emerging firm capacity options, whether they be hydrogen, advanced nuclear, CCS, and those could also help lower the cost of meeting these deep decarbonization targets and lower the risks. And we know that we're going to have to build a lot of infrastructure, but we can do it. So that's the high level of this study, and now Brian's going to tell us how things are changing to get us there. Great, thanks.
Thank you, Liz. It's a great summary. For anybody that is interested in going into more depth in the study, I would highly recommend that you download and read it. It's publicly available. There's a tremendous amount of great information in there. I know I have some follow-up questions. I'm sure you all do as well. What I'd like to do now is introduce Brian to run through his comments and presentation on New Hampshire's transactive energy rate pilot. And then we'll do a full Q&A session at the end.
Is this the? Oh, how's this? I'll take the mask off too. Is this the advance the slides? Great. Hello, everyone. This is awesome. Haven't been to a conference with people in almost 2 years, so I imagine that discussion's gone on already. So this is great. Brian Callnan, New Hampshire Electric Cooperative. We serve 118 communities in New Hampshire. We've got about 85,000 services out there and roughly 70,000 members. We are a cooperative, an electric cooperative, member-owned, nonprofit. So we're member-driven, and we try to find what the members want. We try to deliver. So I'm going to jump into a pilot that I would like to say is answering some of those questions, but it's just on the surface of what Dr. Mettetal just talked about. So New Hampshire Electric Cooperative, we have a strategic plan that's been in place since 2017. It's a 5-year strategic plan. It goes out through 2022. Part of meeting one of those particular goals, there's 4 of them, I'll talk through that, is something we're calling the transactive energy rate, or TER, and I'll define that a little bit better. And then I want to walk through what's the purpose of that. It talks about some member benefits. So we're hopeful that because of those member benefits, folks would be interested in jumping onto this pilot. And I grabbed a nice quote. I don't know if anybody's had a chance to read through that, but this is from someone at a small auto manufacturer called Volkswagen. What struck me from this quote is when you talk about the electrification, and Volkswagen's really pushing forward with this, is that kind of in the middle of that quote there. Between 2025 and 2030, their contribution, not all auto EVs that are out there, just their contribution to it, is 1 terawatt hours worth of storage. And according to Michael Jost, that's more, I haven't checked that, but that's more than all the hydroelectric power stations in the world. That's just phenomenal. Okay, I'm going to walk through one element of our strategic plan, which is the business model. There's a lot of words on this slide. Read them if you'd like, but I'll give you a quick high-level summary. There are 4 elements to the strategic plan. Voice of the member is one, and the first one, right? That's why we're here. Business model is planning on changing or modifying the business model so that members can interact with the cooperative in a different way because they want to. The other section is we've got financial stability. Not really all that great to have an electric co-op that's not financially stable. So that one's always one that you're pushing forward. And then probably one of the biggest ones is organizational effectiveness. You got to find the right people to help move us forward. You got to find people that are smarter than yourselves, bring them in, and try to come up with some new ideas. And really, it's about the empowerment and the engagement of the employees at the co-op that we're focusing on. Kind of a 200 CEO kind of view. There's about 220 employees, so I should say 220 CEOs. What I'm going to talk about is in that third bullet, the transactive energy rate. I'm going to refer to it as TER because transactive is got all kinds of meanings. I imagine we could probably come up with 5 or 10 just by going through it. We define it more as a business model where the member can interact in a two-way communication with the co-op in a different way. We know transactions. We've been doing them for over 80 years. We serve our members, and we serve them electricity, and they pay the bill for that. In this way, we want to transact with the members in a different way. So the member can actually start providing services to the co-op. And by providing services to the co-op, they're providing services to the other members. So that's our view of transactive. There's many other ones out there. The pricing signals I'm going to walk through are just the foundation of that. You need to build onto something. So we've chosen a price signal to help our members interact with us in a different way. And I'll walk into that a little bit. This is just a nice graphic, I think, that just shows that the co-op, our members are interested in installing more and more DER. And DER is distributed energy resources. That's a lot of different things. You can talk about efficiency as being a DER. Solar PV is what probably comes to mind for everybody. EV chargers, definitely. Thermostats, batteries, there's all kinds of different things that we can throw into that bucket, and there's more and more of it coming on. And members want it. It improves their lives. So we want to help that. This slide just shows that we're just in the beginning stages of here. So we're working towards it. We're doing our best, but these are baby steps, and we're doing pilots. But we are taking some action. We don't know the adoption rate that's going to occur in our service territory. We think we can help improve it, but we want to be ready for when that gets ramped up. Okay, I'm going to walk through a quick example of this. So what is it? It's a single price. I think there was a discussion earlier I heard today about kind of real-time price signals. So if anybody was at that, this is not that, but it's similar. This is day-ahead price signals, so very similar. A 24-hour interval price that a member can plan for, which is the difference between real-time and day-ahead. A member will see this the day before, and they can go ahead and schedule their devices if they're interested in doing that. We want to make this is a pilot. We want to make this pilot available not just to the home, but a device. And that's important because you may not want your whole home to be on some of these high cost hours. So we want to be able to pull out the devices that you can control. I don't know if anybody has any teenagers, but I do. And I don't necessarily want to go away for the weekend and have to pay for a high cost because my son had a party at the house and everybody was in the hot tub. So that's something that's out of the control, but you can control your battery. You can control your EV if it's plugged in. You can control your thermostat, and you may just want that on there. So there's definitely some technical hurdles to that, and we're trying to work through those. Another important part of this rate design is it's just that, it's a rate. It's really not that special. It's just a rate that changes all the time. We will not be controlling things. That's not the idea, is to control devices. It's to give the member power to control their own contribution to the grid or to our distribution system. Now this is one element, it's an unbundled state, so there's a lot of different costs that go on your electric bill. This does not include the distribution costs. And when I say distribution costs, those are the costs to keep the poles and wires in great shape and all the people making sure that they're delivering great service, and the buildings and the trucks to get everybody out there when we do have a disturbance in the system. I'm going to walk, the next slide has this in two, so it's a whole 24-hour day. But to read this table at the bottom, the first line is simply the month. So this is January 21st, 2019. Hour ending is a strange electric term. I'll look at the hour ending 3 there. What that means is it's the hour between 2 and 3 in the morning. The rate is what the transactive energy rate, or the TER, would be, and that's 9 cents per kilowatt hour there. And I'm using an example of a battery. And in this example, it's a charge. It's not in parentheses there. So it's saying that I've got a battery and I want to charge during those hours because I looked at the prices the day before, and that was a really cheap time to do it in that day, and I really wanted to make sure I charged my battery up that day. Here's a full day. So I walk through the top one. The member charges the battery, pulling energy from the co-op during the lowest cost hours for the day, and they chose those hours. And then you can see that in this particular situation, the member wanted to, they saw that the price signal was strong enough for them that they really wanted to make sure they discharged that battery into the system. Just like a net metered system, you could discharge the full capacity of the battery. It could serve first the load of the house, and then it could actually push into the system just like a net metered PV system does today. And in this particular example, $2 was made. It's a lot of little ones to make an example here, but that is the overall idea. So why would someone bother doing this? $2 doesn't sound like much. So you got to add all these things up. I've got looks like I've got 5 different examples here. I'll focus on the first few. And there is a typo, so I'm sorry. So the first one is a home battery. We used a Tesla battery here, just because that's a pretty popular one. In this example, I used 5 kW, so that's a Tesla battery can push out 5 kW continuous for multiple hours. They've got 13.5 kilowatt hours worth of storage there. And by managing that battery to try to maximize the amount of profit for that battery itself, you could, at the end of the year, end up with $1,100 worth a year for the credit. And the concept of that credit is it'll show up on your bill, but it'll help buy down that investment for folks. And we think that might help increase adoption if members want to have batteries in their homes. Now this is just, when we talk about batteries, this is just the transactive energy piece, right? The ability to, or the TER piece. A lot of members will install batteries for completely different reasons. Resilience, to make sure if there is an outage, which we try to keep as little as possible, but they can keep their home or their freezers going. So this is an added benefit to help improve members' lives there. And then EV charger. So this is the third one down is a vehicle to grid personal vehicle charger, but this is just an EV charger so that you can charge when you want to fill up your car. And this is using 13,500 miles a year. And the 6.6 kW, I imagine a few people probably know what that is. That's a Nissan Leaf. So that's using a Nissan Leaf 62 kilowatt hour battery. If you choose the lowest cost hours to charge your car and you drove 13,500 miles, $120 a year to fuel that car. That's pretty inexpensive. And it's inexpensive anyway to fill your car on electricity. So I put a comparison there. I said, if you're not doing the transactive energy rate, you're only going to spend almost $400 anyway. So that gives you the difference. The next one's a little bit more interesting because it's a little bit more like the home battery. That's a vehicle to grid personal vehicle charger, which they do make those. If you purchase that, then you have the ability to use your battery in the car and provide services to the distribution system if you want to. So it looks like just like a battery, it's just got wheels on it. And in this example, it's very similar to the home battery example. You could drive 13,000 miles and then still end up with a $1,200 credit after you've paid your fuel bill. So these are just, I won't go through the rest of them, but you can see there's some other examples. And this is just indicative, which is a nice electric term, right? These aren't guaranteed views, but it's to give you an idea of the amount if you wanted to participate in this system. Oh, I think that's it for me. Thanks very much.
Awesome. Thank you, Brian. So great. So I think with that, I'd like to open up some Q&A, and I'm gonna start with one for Dr. Mettetal here, because one of the things that I found most interesting about the study is just really the importance of capacity, right, and resource adequacy, making sure that as we have more and more renewables in the grid, that we've got the capacity to meet these sharp ramp rates, to maintain reliability, because even the most ardent environmental supporters out there want to make sure that the lights come on when we flip the switch. And I'm curious to understand just how does the modeling, how does it look at essentially the capacity availability of different types of generating resources?
Sure, can you hear me?
Sound great.
So one thing I didn't talk about much during this presentation, given the timing, was the loss of load probability modeling that we developed to support basically estimates of effective capacity contributions for all of the resources that were offered as supply side options to model. So I guess without getting too technical, we know that New England maintains a 1 day in 10 years reliability standard. We held that standard constant through our study, and our loss of load probability model basically looks at historical weather, historical wind, and historical solar generation, and simulates the electricity system thousands of times and looks at the ability of, in particular, renewables to provide effective capacity. So how much, if you remove perfect capacity from your system, how many renewables do you need to hold reliability constant? And so you come up with basically a perfect capacity equivalent for your renewables. And so in the study, you'll see what are called ELCC curves for renewables, which is basically the perfect capacity equivalent of those renewables. So I think wind starts off around 20%, but solar, given its profile and its generation in the middle of the day and winter, a winter evening peak, has basically very little, almost no capacity credit by 2050. But as you saw, it's still the model still builds a lot of renewables. It's just building them for energy, not capacity.
Excellent. All right. Thank you.
I guess this was a question. I guess a question about if you had anything in your models that would show, right now we have no time of day pricing in New Hampshire. So do you have any information from other states where that's been available, the ability to shift load off of peak as a way of cutting the capacity that you need?
Yeah, no, absolutely. So, we have looked both in New England and in other settings at the role of basically managed charging on the EV side, or preheating or pre-cooling in buildings. And I think the modeling, the research frontier is looking at sort of like what's the firmness, or like how perfect, how reliable is that, the ability to shift. And what I can say is, for the transportation, we assume, pretty significant portion. So like 70% of EV load, for example, could be shifted out of that peak hour as firm. Other places have seen, that number vary from 0 to 100%. I don't know that we have the answer yet, but I think, time of use pricing and incentives to move charge around will definitely be really important for managing that peak.
Yeah, I'll add that an area we're particularly interested in is in grid enabled buildings, right? So we see a lot of particularly CNI buildings with more and more sophisticated energy management systems, easily with the ability to ramp up, to ramp down variable speed drives, to pre-cool, to set back in response to some of these price signals. So I know that's going to be a big aspect of kind of demand response, of load flexibility, some of these assets that we're talking about. And I know, Brian, when we were prepping, we also talked a little bit about kind of the role of distributed energy resource aggregators, right? So the folks that are out there, the revisions installing storage, being able to aggregate together, be able to respond to some of these price signals. So I guess, Brian, maybe a question for you is kind of where do you see the role of some of these DER aggregators fitting into this grid of the future from the co-op's perspective?
On, how's that? Oh, I think it's, we think it's critical. Going through that rate that we just showed, we don't really see a lot of members getting all excited to wake up the next day and go around and schedule a bunch of stuff. In order for that to happen, you need an aggregator that can help play that role. The aggregator is going to develop software, develop communication, make sure they're following all the protocols so things can happen, and then deliver those services for the member. So I think to that, Matt, the aggregator, in our view, is critical in order to make that work. Adoption won't be as quick without it.
Agreed. We're having some audio issues, so we're going to use the mic and hand this back and forth from here on. Are there more questions from the audience? Great, step on up.
I had a question for you, Dr. Mettetal. So, you spoke of carbon capture technologies sort of being necessary to reach net zero for New England. I mean, how viable is the implementation of those technologies? I imagine the energy required for carbon capture would strain, our grid systems, and we would need more renewables to sort of support those efforts. Do you foresee a lot of challenges with that implementation?
Yeah, I think that, sorry, I think carbon capture technologies are just one possible option for helping us get to net zero. I think it's, for example, in New England, there's no real place to store carbon, and piping it is a whole nother infrastructure hurdle. I think there is a lot of exciting emerging technologies, and I don't think we know who the winner is yet, but I think CCS, advanced nuclear, hydrogen, all of these kind of like bucket of emerging technologies any one of them could dramatically lower the cost of us achieving net zero. I think I would agree with you that CCS is one that has more hurdles to true commercialization at a cost that's anywhere near competitive.
And most plants, from what I understand, they really have to operate on a value added product model where it's really carbon neutral and not carbon negative, right? So I guess getting the funding, you would have to really subsidize it from a governmental standpoint, I would imagine.
Yeah, I think that's right. And I mean, I also think we didn't really talk about it much here, but you know, at some point, direct capture might become a more, it might come down in cost, but we just don't know. Yeah.
Thank you.
Hi, my name is Rick Lebrecht from Eversource. Thank you both. I got a question for each of you. Brian, you'll get, I think, the easy one. What kind of special metering or communication challenges do you have in rolling out these kind of programs? And then the question for Dr. Liz. I like to follow the money on these studies, and I saw you say Calpine funded it, and then there's a slide that says something about the cost in 2050 would be 19 billion per year more expensive. I think it's if combustion turbines and combined cycle gas units were retired. Is that are we supposed to believe those units are still going to be running in 2050? And I guess I've been hearing about these multi-day storage batteries, and their pitch is they can replace these peakers. So I wonder about that. But thanks.
I'll start. Yeah, sure. So, yeah, I mean, the study was funded by a natural gas company, Calpine. So, but they were not involved in the actual work. And if you look at the report, you'll see we do have a pretty robust advisory group that did, you know, weigh in on the modeling assumptions with representatives from the utilities and NGOs research that said. So I do think if long duration storage came down in cost, it could be a source of firm dispatchable generation. I think what we need is we need firm capacity of some sort by mid-century to ensure reliability standards are met, whether that's, you know, a 100-hour battery or a hydrogen, really any form of firm capacity, advanced nuclear, any one of those could play that firm capacity role. Our modeling base case started with, you know, what's commercially on the market today. So there, you know, it's biased towards combustion turbines in the sense that they're there, but certainly, you know, the emergence of long duration batteries or a zero carbon fuel would could play that role.
Nice to see you, Rick. So just to remind everybody what the question was, it was on communication protocols and what kind of issues have we run into. And communications, there's all kinds of issues with that. So there's all kinds of problems there. We are trying on this entity with a New Hampshire broadband. I hope some folks have heard about that. Trying to connect more and more of our members. This type of technology that we talked through to use this rate would require some kind of internet connection. And some folks don't have that. So not everybody would be able to participate unless you had an internet connection. So the actual protocol that we are using and developing it with is something called OpenADR. I'm not an engineer and I'm really not all that technical, but it's kind of a demand response protocol. And we've got some, we have some, I don't want to say pilot, we have some samples of it or examples of it where it's communicating just excellently up in Colebrook. Up in Colebrook, we had a bunch of folks on a water heater program, and we lost the radio tower. some years ago. And so those folks could no longer participate. So instead, we put up some open ADR devices up there, and we're able to connect that using that protocol with some software we have in-house. So far things are working quite well. One other thing I wanted to mention on the aggregator piece is I imagine there's some aggregators in the room. So if there's any folks that are interested in how this will work or how we think this will work, we kind of need to hear from you. So if you don't mind giving us a call and letting us know what might work best for you, that will help adoption in our service territory.
Thank you. Any other questions from the audience? Sure.
Hey, Ethan Goldman from Resilient Edge. Brian, so I've got a question about the sort of transactional part of all this, and I'm sort of trying to think through like what's the longer term, how does this expand into more things, and I'm seeing a lot of the like time of use traditional rates now getting mapped seemingly onto individual appliances, and wondering what is the trajectory you see that going down, because it seems like in some ways it's adding complexity, because now you've got to meter individual appliances. It's adding potential for gaming, because if I have 2 heat pumps upstairs and downstairs, I can put one of them on the rate and then let the other one carry it when things are, I mean, not that I'm necessarily scheming to try to steal from my utility, but I'm just wondering, like, what are the advantages you see of going down this path of actually having the individual appliances versus just trying to come up with a whole house model where customers can really think about how to optimize long term in terms of weatherizing and electrifying and really shaping their entire load rather than trying to fit things into these buckets? And does any of that actually start to get at the sort of transactional part of transactional energy that I've heard of probably a couple phases down the road, where we have a market where the rate is actually set based on how many devices and how much load can show up at different times? Sorry for packing a few questions in there.
I think I'll miss a couple of them, so I'm sorry if I do. One, I think, was whole house and device. Why go that route? As I was mentioning in the presentation, a time of use rate is both a benefit and sometimes can be looked at as a penalty. Some of those prices can be quite high, and if we're trying to make sure that adoption is increased, and we want to remove barriers from folks that are concerned that they may actually have that rate become a penalty because they weren't able to reduce their load during those high peak hours. So by pulling the device out, that will give you the control of something that you can control. You say it's a very cold day, and you have a battery. You can actually use that battery on that rate, but you might not be able to offset your entire load with that, so your home is going to be impacted by the other rate, by the B rate. Our residential rate is what that is. So the reason to try to come between a device level and a whole home in the pilot is to try to remove some of those barriers on adoption. You also asked about marketplace. So we need to get started. This was the low-hanging fruit for us to try to set up something that could turn into a marketplace down the road. Getting people comfortable with a variable rate that can change 24 hours a day, that's a pretty big hurdle in itself. So we want to attempt that first, leveraging the investment that the members have already done with our AMI meters, our interval meters that are out there in the system, and also with a transaction that they're used to, which is with the cooperative. So we can make it as seamless as possible by just using the same communication structure that we have today, which is through a bill. You had a couple other ones in there, but those are the main ones, I hope.
No one else is rushing up. Maybe I'll add a follow-up one then, since you are starting with just the appliances, is whether you have used the whole house AMI meter to try to validate whether the benefits that you're paying the customer for are showing up in terms of the change to the overall load shape that's affecting your overall member costs.
Okay, so I did also want to make sure to be clear on the rate. It's an option, right? So you could choose to enroll your entire home and use the meter for that rate if you wanted to. That would be great. It makes things a lot easier if you do that, because the communications are pretty simple. We know how to read meters. The other part, if you bring in the devices, it adds some complication, but those are some hurdles I think we can get over. The reason for that, I think you talked about what you're paying folks, and you also brought in some kind of, I think you used the word scheming, right? What we have based this rate on is a full pass-through for avoided costs. So we know our hourly costs, and that's not just energy costs. We throw additional costs in there. And we are transferring that cost or value, if you're producing something or delivering services to the cooperative, to the membership versus buying it from somebody else, buying it from ISO New England, buying it from Shell. You name your company that we purchase from. What that means is that if that member doesn't show up and produce energy at that time because it was a high peak time, the members are not really, there's no cost shift, because we're still going to be sending that same dollar that we would have sent to that member. We're going to send it to, say, ISO New England and buy those services there. So that is the reason to try to keep it on an hourly basis. So it makes it so it's a much cleaner avoidance of cost shifting, which can sometimes be a concern.
Thanks. And Brian, so we've talked a lot about batteries and EV charging. And in Dr. Liz's presentation, she talked about the push towards electrification in general. We expect a significant increase in the overall system peak, right, in the next 30 to 50 years. I guess a question for you is just from the perspective of the co-op, how are you looking at distribution system planning to be able to deal with some of these increases, likely increases in total peaks, total electric demand? And obviously this type of rate is one strategy, right, to try to move people off of those peak periods where we know the peaks are already going to be exacerbated. Just wondering if you could just talk generally about kind of your thought process around distribution system planning to deal with greater loads.
I wish I was an engineer. I'd be able to answer that better. But I do know that the co-op is working heavily in that space. We've done a lot of investment in our system in order to make it as reliable and as resilient as possible. That's when you have disturbances in the system, if you can pull the power in from another area and lock that out, that helps keep those members going. So we have been doing that over the years. There's nothing new there. Tree trimming might not sound super technical. That is massive. So keeping those trees away from those lines, that helps everybody keep everybody going, right? It keeps the electricity flowing. When it comes to additional DER being adopted throughout the system, we are looking at and we are installing additional DA or distribution automation. So those are devices that can be on the system. It can help either reroute power or stop the power outage from moving beyond beyond the area where it's occurred. And that allows us to do things a little bit faster because they're hooked up to our SCADA system, which is kind of our control system in the control room. Another thing that we've invested in is a map. It's a hosting capacity analysis map that we update every year. And what that does is that has how much can our members put on our system in specific areas of the system. So on a particular feeder, you can go on our website and click on that map, and you can see whether or not there would be significant investment that would be needed for, say, a PV system. Just by doing that map, we had to pull in significant engineering in order to figure that out. And because we're upgrading it every year and updating the map with new investment, so it can show the new investment that our members are making in distributed energy resources, we already are getting smarter about where those pressure points might be, so we can help fix those. So we're trying to prepare ourselves for what we think will be a wave of distributed energy resources on our system by doing some investment today.
Thank you. I think we've got time for one more question. Are there any more questions from the audience? All right. Well, I've got a final one for Dr. Liz then. So you looked at a couple of different scenarios. You've got the alternative low carbon fuel scenario. You've got the electrification scenario. And I guess my question for you is, how do you view the role of policy in helping to shape the development of some of these scenarios?
Sure. So I think there is going to be some economically driven transition to, particularly on the EV side, where we think we're getting closer to cost parity, and but it's really going to need to be policy that gets us anywhere near the targets we need to get to. So I think whether that's incentives for heat pump adoption, or EV incentives, or the role of potentially utilities or others, states in building chargers. I think we kind of have to push along on all fronts to get there. I think probably on the building side, ultimately it's going to come down to codes and standards of some sort to get. I don't think the economics alone will support complete building electrification in New England in a cold climate, at least in the near term. And I think on the electricity sector side, whether it's ramping up RPS, whether it's a carbon price, whether it's a fuel standard, there are policy levers out there, but you certainly need policy to send the right price signals and to get us towards net zero.
All right. Well, thank you to both of our speakers. I thought they were fascinating topics. Did a great job. It's certainly a complex topic. Again, for anybody that is interested in diving a little bit further into the study, it's a great read. A lot of interesting information. And otherwise, just thank you all for attending, and I hope you have a great rest of your day.